Good morning. Is it the physics angel come to tell us about the right-hand rule? No, sorry, it's just me. Look at my awesome setup. This is my camera stand. Here we go. I'm going to put the camera right down here on so we can focus in on the right-hand rule. So check it out. This is my right hand. Well, actually, this is the right hand of an orangutan, it looks like, with a long palm. But if you take your right hand and you align your fingers in the direction of the magnetic field B, maybe I could draw that a little bit more clear. If your fingers are in the direction of the magnetic field and your thumb is in the direction of the motion of the charge, out of your palm will come the force, the direction of the force on that charged particle. Okay, so, and of course that's the force on a positive charge would be coming straight out at you right now. If the magnetic field is this way, the motion of the charge is this way. Okay, let's try to apply that, see which way the force would be on in these examples. Okay, see all these dots? These are like arrowheads coming straight out at you. So if I'm going to take my right hand, I've got to take my fingers and point them straight out at you. And then I've got to take my thumb and align it with this charge. So let's see. Fingers go this way, and I've got to rotate my hand all the way this way so that my thumb is in the direction of the motion of that charge. My fingers are coming straight out towards you. That means the force on a positive charge would be out of the palm. But look, I've got a negative charge. So the force would actually be out of the back of the hand. It would be to your right. I should have started over here a little bit more direct. I'm going to get my hand in the direction, my fingers in the direction of the magnetic field, my thumb in the direction of the motion of the charge. Since this is a positive charge, the force is going to be in the direction my palm is pointing. So the force would be straight into this surface. For this one down here, see if you can guess. Okay, the X's mean that the magnetic field is going straight into this surface, so it's going straight into your smartphone or your computer. Line your thumb up with the direction of the charge, and then look, the force on this positive charge would be straight up, right, and from the hand, or from the palm. All right, what about this one? This one your hand breaks, doesn't it? Because your fingers go this way, but your thumb is supposed to go in the opposite direction. What do we do about something like that? I don't know. Let's see. Let's go back to how you calculate magnetic force. That's the magnitude of the charge times the direction, times the velocity, crossed with the magnetic field. Okay, now remember, a cross product for two vectors is going to give you another vector, right? It's going to tell you what direction your force is. But also remember that the cross product is would lead you to the sine of the angle between these two. Well, the angle between these two in this case is 180 degrees. And the sine of 180 degrees, that's 0. Okay, so there would be no force on this charge. This charge would just keep on moving, not even knowing that it's in a magnetic field. Okay, what about this one? See, this one's interesting because, actually, let's do this one first. If we go down this one, get our fingers in the direction of the magnetic field, get our thumb. Our thumb's not perpendicular anymore, right? It's kind of in this direction now if the thumb is in the direction of the speed, or in the velocity rather. But isn't this velocity, there's a horizontal component to it and there's a vertical component to it. Okay, this horizontal component, it's in the same direction as the magnetic field, there would not be any force due to the horizontal motion here. But this vertical motion, this vertical component of the velocity, when you cross that with the magnetic field, you would get a force, and that force would be, let's see, that force would be straight out towards you, right? Here's your magnetic field, that's where your fingers go. V is in the direction of your velocity. Out of the palm would be the force on a positive charge. Okay. I wanted to call your attention to this one too, because I want to talk about what's going to happen to this charge moving through this magnetic field. First off, see if you can figure out what direction the force would be on the charge while it's right here. Right? Fingers coming straight out towards you, because that's what the little dots mean, that the magnetic field is coming straight out of your screen. Put your thumb in the direction of the motion of the charge, the velocity of the charge. That's this way. So that means the force is straight down. Okay? So I would have a force that is perpendicular to the motion. What do we call a kind of force that is perpendicular to the motion? It's actually a centripetal force, right? Forces that are parallel change the... Thanks, Rosie. Forces that are parallel to the motion, they affect the speed. But forces perpendicular, they affect the direction. So what's going to happen is this charge is not going to be moving to the right anymore. It's going to be moving to the right and down. So maybe it's at this position, and it's moving in this direction now. Can you see that if you put your right hand rule, you're also going to get it? Your force is going to be perpendicular to that velocity. And you're going to have this, what do you think the shape of the path of this particle is going to be in this charged particle in a magnetic field? It starts here moving in this direction, perpendicular to the field. It's actually going to move in a circle now. Right? It's a centripetal force. It's going to be moving in a circle because the force is always going to be perpendicular to the velocity. The magnetic force is always going to be perpendicular to both the magnetic field and the velocity.